decision tree model, you remember that we talked about apple and orange sort of thing. We use the decision tree in that example. At the end of this set of slides, we want to know types of classifiers that you can have. A classic machine learning problem defining a hands-on project and learn more about it and having one conclusion. The thing is, we have different form of, what do we call it, machine learning, like artificial neural networks, convolutional neural networks, support vector machine, decision tree, random forest, boosting algorithms, and you name it, many more. But the thing is, here, because of the ease of usage and interpretability, we are going to use what? We're going to use decision tree. And there's one classical kind of problem that it's iris dataset, which has 150 lines of samples. So we have 150 samples, different kind of iris flowers. So there are three types. One of them is versicolor, virginica, and setosa. So the first 50 belongs to one category, the second 50 belongs to the second, and so on and so forth. So in order to simplify the case, we can say the output for the first is 0, the output for the second is 1 and 2, right? With different features. Guys, it's not the problem of my English, it's totally the problem of my knowledge in bio, which is close to 0, that I don't know the sepal and petal. So one of them, I just know the flower at best, okay? And the only flower that I can recognize, not to tell you any lie, is rose and at best tulip. That's these two, okay? So don't ask me any more about these kind of things. I know that they started measuring this. Apparently there is one person that had enough free time to go and measure every single part of these poor flowers and said, okay, these guys have these kind of specification, these guys have this. So if you see that the features are there, it says that the sepal length, sepal width, petal length, and petal width. And the first category belongs to setosa, which is this guy if you see. And the second one is versicolor, and virginica is the last one. They're all iris, right? So if you go to Wiki, you can find those kind of iris flowers. Let's go here. We want to import data set. Because it's a kind of classical data set, it's like MNIST for handwritten digits in, what do we call it, in deep learning. Something like that. In machine learning, we use this one as a classical data set. So we train our classifier, that's the part that you're familiar with. Because I told you, this is one of the classical data sets. You don't need to read a CSV file or tab separated file or something. You simply say from scikit-learn.data sets, please import load iris, right? And then you say, okay, load iris, and place it in one variable, which that variable now contains a data set. A data set in a language of Python, mostly we use it inside the pandas. Okay. Why we use it there? Because for the sake of these two examples, we don't need that. But if you want to work fine and with high performance, you need to have two libraries. These are two libraries that mostly we use. NumPy, which is numerical Python, and also pandas, right? Mm-hmm. And we always use kind of alias for them, like we say import pandas as PD. We say import, import NumPy as, yes, okay. And I have to show, there's something that Satish sent me. You know, always I receive lots of scientific things from Satish. Satish, where are you? Say, just send some hello or some you're here. Okay. Guys, look at this one. Did you get the joke?
Yeah.
If you want to tease somebody, you just, use this alias, like, instead of TensorFlow that you have to say TF, just say PLT, which is, so for this one, matplotlib is for plotting, right? So, yeah, just, that's the nice one. Okay, don't do that. The thing is, for this, for the sake of this example, we just said, okay, we are going to use we are going to print the iris feature names. Iris feature names are these guys. Just to jog your memory, look at this. The first line starts with 5.1, 3.5, 1.4, and 0.2, and that is the first, right? And they are SSPP, right? Sepal length, width, petal length, and width. Look at this one. If I just say, okay, print the feature names, it says that sepal length, sepal width, petal, right? And if I say, okay, show me the target, which are setosa, versicolor, and virginica, right? They're the labels. But the very first row, do you remember I said 5.1, 3.5, 1.4, and 0.2? It's exactly the first row that I said, okay, from the data, show me the first line. And for the target, what is the first one? Setosa. So that's why it shows you the 0, which stands for this setosa. And you can just do the same thing for 50, because from index 0 to 49 belongs to the first category. If you just say 50, it's gonna show you some features for versicolor, and if you say 100 or 120, it's gonna show you the third category, which is virginica. Simply if you just try that. And if you get any different result, don't say it aloud, it's gonna get recorded, okay? Hopefully it is like that. I tested several times. Satish, yes? Awesome, perfect. I invited Satish to just confirm. How about you? It's not working, Ethan? Guys, your internet works?
Yeah. Oh, I think mine
Doesn't?
work. That's why I'm connecting to what's that?
In your room?
To run, yeah, that.
Yeah, it's your room. Right. Cool. Okay. Let's go a little further. You have the code, for sure you have the code here, so don't worry about that. So in the next part I just said, let's just, to the length of iris target, which is 150, this is not that much, the way that you need to. Simply you could say, hey, import pandas, and do what? Just print the content of that, right? But it's a kind of form of thinking C programming while you're typing Python. So it says that for each element inside this range, print this. So we're going to print I and those kind of things. Okay, let's go to the next. That is importing data, and to train the classifier, simply what we did before. You remember, there's just one thing I want to show you here. Satish, I would be thankful if you can have here. Simply, in this example, we just say, if it is 150 total, the examples that we have, we just, what is the index of this one? 0. What is the index of next is 50. And remember, the label or the target for the first one is 0, which is for setosa and versicolor. And 100 is the beginning of the third, which is virginica. What are we going to do? We are going to take these three out of 150. So 150 minus 3 gives us 147 examples. We train our classifier. You remember that we trained it with some apples and oranges? We use the same thing. We say that CLF dot fit
and we use the remainder of the training. And then we use predict. We use predict to see if we get the output for them in the same way. Look at this one. Because I have the features for this, I have those 4 features for this and for this and for this. What I'm going to do after finishing all the process, first, I'm going to show the actual result. This is an example, right? I'm going to say, hey, the target for the index 0, the target for the index 50, and the target for index 100 are 0, 1, and 2. And then I'm going to say, okay, let's use this to predict if it gives me 0 as well. And if what I expect is equal to what I already have, then the accuracy is 100%. Normally, the world is not like this. It's not ideal like this. Normally, we have some labels that we can get up to a certain level of the correct answers. So the ratio of what we get on what we have actually gives us the accuracy. But there's just one thing. I can just work on it and make the accuracy higher and higher and higher. But what is the problem of this concept? I know that you know it. You can just close your eyes and say. But tell me, I can improve the algorithm to work with this data that I have, to work better and better. In machine learning, in deep learning part of it, you have something that they call it epoch. So it's like iteration. So you go 1 time, 2 times, 3 times, and it makes it better and better and better. But what is the problem? Yeah, you start with something like the accuracy of 70%, end up to something like 99.9. What's the problem with that?
It might fail in another problem.
Sorry?
It might fail in another module, another problem.
Awesome. Means that it works with the current data, but it cannot work the same way with out of sample data that I have.
Overfitting.
What do we call it?
Overfit.
Excellent. So, the problem that we could see is overfitting. What if we don't fit it the amount of data that we need to? Then we have kind of underfitting. So the whole thing is like to balance the overfitting and underfitting. Kind of trying to keep balance between generalization, right, and optimization. General optimization.
So what do you use as a reference point to see if it's too much or too little? What
Excellent. That's an amazing question. Guys, up to this part was free, but after that you have to pay for it. How about that? This is the content of something like 4 hours of teaching. But let me just tell you one quick thing. But accept this from me that we are going to get to that in 2 consecutive sessions. How can we find a kind of nice point to say, okay, enough is enough. You're not going to use more epochs. Because technically, if you use more iterations and more iterations, you're going to make your project work perfect with current data, but it's not going to work the same way with the out of sample. How about this? Look. Normally, we have one part of our data as testing. So let's say this one should be out as 20% and 80%. But that 80%, we can say, okay, let's use another 20% of it, okay, as the validation data. And that validation data is something that we check. Look, we train our model using that 60%. But we check it with this one, and we see, okay, what are the things that we can check always? How far we are from the perfection. We call it loss. The loss is from the sky, then it goes down, 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 and it goes like this to 0 for this part, for that 60%. But if you use the same thing, you see that, okay, it goes maybe something like this from here, but after a while, you are not engaging this one into giving feedback to your model. So then it's going to be like this. This is the optimal place for it, right? So this is the validation, but this is simple kind of cross-out validation form. Is there any other? What is wrong with it? Imagine that apple and orange. You have 80 samples of apples, and you have 20 samples of, I'm saying one extreme example that it's gonna, just show you the problem of this approach. You are learning with this part, but you want to test it with some labels that you haven't trained. This is going to work awful. So what could be the solution for it? Okay. The best solution is, I consider the whole as my training. I take 10% of this out. I work on the 90%, create a model, bring that 10% in, and now you take the second 10% and you concatenate this part plus this part, and you do it again and again and again. So that one is 10 cross-fold validation. If you use 5, it's going to be 5 cross-fold validation. It's going to make it better. The best is to shuffle the whole thing, right? And we have lots of them. So just please accept from me that we have some ways to overcome the overfitting, but we're going to talk about it later. Okay, let's get back to this one. Now the camera should turn, Satish. I'm here. Yeah. Look, this part is the, what we say that is, I have to, I guess the best is to show you the whole code. Look, we said the test index for the first example, I said let's take out 0, 50, and 100 as the first sample of each category. So I said these are the indices of the test index. And then I'm going to say, okay, from the training part, I'm going to delete these guys. Oh, I don't want to mix training and testing. We never do. And then let's go to this part. I say, okay, iris.target test index. This is the test. What are they? 0, 50, and 100, right? And we do the same thing for the targets. So we have the actual labels. What's the next part? We say, okay, CLF equal to tree, the decision tree classifier. This is the empty box yet. Then we say, okay, this is the training. Exactly like what we had features labels there. We have training data and training target, versicolor, setosa, and virgin. So this is going to train based on 147 samples that we have, right? And then let's go to the next one. Now it's the time to, the train is done. That's the time that we want to know how it works with the testing part. So let's get back to the code. We already talked about here. We get to this line. Do you remember that I said that let's have some cheating? Let's say, okay, what could be the labels that we took out? Do you remember that? This is the test target. Means the actual labels that we know. This is 0, this is 1, and this is what? 2. Okay? I mean 0, 1, 2. Look at the result here. Here, please. Not surprising. It's going to show you the actual labels that we eliminated, 0, 1, 2. But in the next part, look what we added here. We said, okay, CLF means classifier that we created. Go and predict. The test data means the columns that I took out. And I expect you to predict what could be the labels, and it gives me 0, 1, 2, which if you compare with the actual things that we took out, they are equal. So in this specific case, we have 100% accuracy, which is far from the things that we deal with in daily life, right? Is there any question here? Okay, by saying that, I just wanted to have visualization, what's happening, so I just copy and paste this code from the website, and for doing that, you need to install GraphViz. So I just showed you, and this is the updated version. You go there, you install, these are just, some next, and you need to have this as a part of your environment variables. Guys, it took me something like 1 or 2 days to just go through all this and find all those error messages, because the guy who did this had already the library on the computer. He didn't bother to just, I was starting that, right? I'm not sure, I didn't try this using these Keras. High probability Keras doesn't need an installation. But anyway, you bring this guy to environment variables and add it into the path. So technically now it is accessible. You just say new, just don't forget to have that backslash at the end. The thing is, these are the prerequisites, like install py.plus and py.n-ng. And if you want to uninstall it, you simply can do the same for uninstalling. Anyway, the thing is, the first part that I copied and pasted, these are the lines. You see that it says that the tree.export GraphViz CLF out file none. It is going to give you a PDF file into a place that you have your other files. So it uses the file and gives you something like this, a graph like this. I didn't like that. I expected something more colory. So I have stolen the other code from the website and I replaced it. So here is the file. You are not now, there's no intention to know the things, but look at this. Actually, this is the classifier that computer generates for us. And that's what's happening behind the scene. So look, what was the first, if you have downloaded the file, can you please tell me what is the length of petal length for the, okay, so let's go together.
I can't get it now.
It's here. Does anyone have this guy that, I'm talking about this data set. So look at this. The first petal length says it is 1.4, right? So I'm not sure if, okay, look at this one. It says that, is it less than 2.45? For sure, 1.4 is less than 2 point something. Yes, then it is true, and it says that the class is setosa. We already reached to the leaf, which is the final answer. For number 50, if you go, you're gonna see that no, it is not less than, if somebody can reach to the number 50.
Yeah, got it.
You got it? So what is number 50? What is the petal length of number 50, which is?
1.4.
Oh, no, then it is 51. So, because then the index you talk is?
4.7.
Okay, because that was the last line of the.
Okay, yeah, true.
Yeah, setosa. So now it is here. How about the petal length? What is it? Sorry, petal width.
Petal width is 1.4.
1.4, so it is less than this. We go here. How about the petal length?
Wait, petal length, I told you before.
Yeah.
It's 4.7.
4.7. Is 4.7 less than this? Yes. So we get here. How about petal width again, please?
1.4.
1.4 is less than this, so we get to the leaf and it says that it is versicolor, the second type, right? Am I right?
Yep.
Excellent. So that's how it actually works. So that's how it creates. We didn't touch this. It is created by the decision tree algorithm, right? But finding how we can just, manage this is not an easy job, but that's how it works. By saying that, you have a kind of nice feeling of what's happening behind the scene. Yeah, I just showed some examples, and look at this one, for example. This is how we traced for the second. You can test for 101 to see if it goes the other way, and it shows you, for example, Virginica here or here, right? By saying that this one is done,